IRF, and so we can go.
Okay, thanks. So hello everyone, I'm very happy to be at this week, and I'm going to talk about a work which is a joint work with my two advisors, Paul-André Mélès and Sam van Rol, and about profinite words and profinite lambda terms. So I'm a PhD student in the beginning of second year, so since September 2021, and I'm working at IRIF in Paris. So there are two different kinds of automata which are well studied and well understood in the community. It is a deterministic automata, which we can relate to the fin set category, and the non-deterministic automata, which is linked to relations between finite sets. But there is a new kind of automata, which is called higher order automata, which instead of recognizing words, recognizes lambda terms, namely programs, which can have a non-linear structure where words are like some kind of recipes, like apply A, then B, then A, etc. And programs are much less linear, and there are new kind of automata recognizing programs, namely lambda terms. So our goal was to adapt the profinite methods that are very well understood for the case of deterministic automata to this new frame of higher order automata, and to have a notion of profinite lambda term, which would have some nice properties. And so I'm going to present this contribution that there exists a notion which generalizes profinite words to profinite lambda terms, and which is adequate in some sense. So let me start. First, about lambda terms and words. So I'm just recalling here the
Sorry, is that just us? Does anyone else have Vincent?
It's also cutting out for me, yeah.
Okay, cool. I'm glad it's not just us, that's all.
Yeah. Yeah.
That's really annoying.
Yeah.
Frozen for a bit.
Yeah.
Sorry?
You were frozen for like 10 seconds or something like that.
Ah, okay.
Maybe, yeah. Yeah, but this slide was, we were starting, yeah, so we were starting with this slide and you were frozen for, okay.
Okay, so perhaps I restart the explanations, no? Hello? Just this slide.
Yeah, now you
yeah, okay.
Sorry.
Yeah. Okay, so so here is the grammar of lambda terms, m and n. So either it's a variable x, or it's a binder. You bind the variable x, lambda x, in the term m, or you apply a term m, which would be some kind of function, to another term that is made of variables and other binders, like that. So you can think of this lambda as some kind of abstraction, and in a way you can replace it with the arrow, like x associates the term m. The types are made of the base variable type O and the arrow, so it will be simple types. And here are the rules for typing terms. So you have a context on the left, and basically if you have a function from A to B and a term of type A, then you can apply and have a term of type B. If you have a term of type B and you have some x of type A in the context, then the function that you will create will have type A arrow B. And if this is more like to have ending derivations, if you have a variable x of type A in your context, then you can type this same x of type A. Okay, so now what is the link exactly with the words? So if it is well known that if you have any natural number n, it can be encoded as a simply typed lambda term as the following. So you take a successor function, but really it's any function, and you take any argument and you apply n times the function s to your argument z. So in this way, you can see that all the natural numbers and can be encoded as lambda terms in the simply typed lambda calculus. But really, a natural number is just a word over a single letter alphabet. So we can generalize this encoding, this chunch encoding. And for example, if we have an alphabet with two letters A and B, and we have the word ABBA, then you can have the associated lambda term, which is the one which takes a function associated to A, a function associated to B, and which produces the application of A and then B, then B, then A over some variable C. So the closed term is here. You take an input, it will be the transition function associated to A, the transition function associated to B, and you produce as output the function which takes any start state and which outputs the end state associated to the run of the word. So now, how can we interpret that in categories? So we have, let's say we have a category C, which is Cartesian closed, which means that we have a good notion of evaluation for our lambda terms. And we can pick for any object Q, we will have an interpretation of all the types. So the interpretation is defined as it follows. So for the base type O, we give Q. And for the arrow type A, arrow B, we have the recursive structure here. So it's the interpretation of A, arrow, the interpretation of B. And so I won't describe how we do it, but we can also have an interpretation of lambda terms of type A. And so Cartesian closed categories are the right setting to interpret lambda terms and to associate to them some kind of semantics in various models. So now let us focus on a very interesting category for automata, because it's a category of finite sets with functions between them. This category is Cartesian closed because we have a right adjoint to the product. And so this gives us that it's a CCC. And so we can interpret every lambda term. And in particular, we can interpret words, which we've seen that are encoded in the simply typed lambda calculus. So for example, if I have a word W encoded as a lambda term, so it takes, let's say that it's over the alphabet with two letters A and B. It takes the transition function of A associated to A, then the one associated to B, and it takes an input start state and it outputs the end state. So the interpretation will be just like that, but in the model, relatively to the Q, the object Q that we have chosen. So now I'm going to talk a bit about profinite words, and we're going to enter their world. So just a few words about this, because I think it's nice to have a good intuition about that. So you have this picture, which is taken from the famous book about Gödel, Bach, and the person which draws, who I forgot the name, but and you have this object at the center, which has different shadows casted by different sources of light. So actually what we say is that we have a physical object and it produces a system of shadows that is coherent. And here, the interesting thing is that the coherence is not obvious at all. But what is interesting is that we can have some tests of the object, a system of results of tests like the shadows. But what if we remove the object? We say, okay, so now I'm interested mostly in the system of shadows that one object can produce, but I'm not going to consider the object in itself as my object of study, but the system of coherent shadows that may be casted by the object. So this is the intuition behind profinite words. So let me introduce it formally. So a profinite word is a family of maps, where M ranges over all finite monoids, which takes for each word, it's a function, a morphism of monoids, which associate to each word over sigma an element of M. And to this data, it associates an element of M. So what this represents is, because it's a morphism of monoid, actually, the data is given only by the images of the letters of sigma. So for each letter in sigma, we have an element of M, which will be like a transition function in the monoid. But what we ask for all this family of maps is that it is coherent. And what we call coherent in that setting is some kind of naturality condition. So if we have P, which is here, and we post-composite by some monoid homomorphism F, then it is the same to then evaluate with the profinite word F sort P, or to evaluate just P and then have F applied. So this is summarized with the following diagram. So every word, of course, induces a profinite word by just evaluating the function P, which lives in here, on the word itself, and it gives an element of M. So now just an example of a profinite word, which is not a finite word, because it's always enlightening to have examples. So in all finite monoid M, all elements have a unique idempotent power. So it's an element which multiplied with itself is still the same. So it's written here. And every element has a unique power if we forbid the n equals 0 power. So it is obtained in general for n equals to the factorial of the cardinal of M. So this is very reminiscent of group theory, in which case, of course, we simply have to take the cardinal of the group and we get back on the identity, the neutral elements of the group. And if we take this and we put it in a profinite word, actually, it's what you get, a profinite word. So you take any interpretation of the letters, you interpret a word W that is given, and you take the idempotent power of this interpretation if in M. And this family of components verifies the coherence condition. And so it's an example of profinite word. Okay. So now we're going to introduce parametricity for monoids. So it's an interesting property. So we introduce monoidal relations, which are relations which respect the monoid structure. So a relation is a submonoid of M times M. So equivalently, it can be said to verify these two axioms. And now for a family of maps UM indexed by all finite monoids, it's the same to be profinite or to verify some parametricity condition. So the parametricity is the following. If we have two P and Q valued in M and N, which are related, which we write in that way. So for every word, the output of P and Q applied to that word are related, then the outputs associated with the family of maps UM will be themselves related. And so this is parametricity, and it's a proposition that we can prove that the two are equivalent. So it's very easy to see that one implies the others because we can take any monoid homomorphism and its graph will be a relation, a monoid relation. So, but the other side is less obvious. So now we're going to introduce parametric lambda terms because we want to generalize this profinite setting, but to lambda terms. That's what we said at the beginning. So recall that for any set Q, we had defined by induction an object A of Q, the interpretation of A in the category by induction. And now we can do the same thing with relations. So if we have a relation, this time a set theoretic relations, and P and Q are single sets without monade structure, we can define by induction on A a new relation between the interpretation of A in P and the interpretation of A in Q. So it's done in the following way. If we have only A which is equal to the base type variable O, then we output R, sorry. And if we have a function type, then the interpretation would be that this relation will relate functions from the interpretation of A in P to the interpretation of B in P to functions from the interpretation of A in Q to the interpretation of B in Q. So this is what is written here. And two functions are related by this relation if and only if they send related input to related outputs. So now we want to have some more formal setting to manipulate all these mathematical objects. So we introduce the concept of double category, which I think goes back to Charles Ehresmann, which can be described in a bit informal way as the data of objects, like for example, A, B, C, and D. One cells which can be either vertical, like that, or horizontal. So we have two different symbols. And now we also have two cells which are squares between coherent pairs of vertical and horizontal arrows. And these squares can be composed either horizontally or vertically. So it's this is what is a double category. And in fact, we can say that it's a category object in a cat. It's some kind of internalization of the concept of double category. And our main example will be the category whose objects are finite sets. The vertical arrows will be the set theoretic functions, and the horizontal arrows will be the relations. And the square, if it exists, is unique. And it exists if and only if the two functions f and g here send related inputs to related outputs. So the existence of a square means some kind of coherence between the functions and the relations. So now we are interested in some kind of double categories because we want to interpret lambda calculus. So we have to have some kind of Cartesian closed structure somewhere. So we say that a double category D is Cartesian if we have some Cartesian structure here. So I'm not going to go too much into that, but you see that there is a Cartesian structure on the vertical category, one might say, and a Cartesian structure also on the squares. So if you have two squares, C1 and C2, which have the same input, let's say domain, then we can construct this square with the brackets C1 and C2, which has the same domain and whose codomain is the product of the two codomain S1 times S2, which are relations in this case. And we have a notion of terminal object. We also want to have the closed part. So there exists, we want our double category to have some kind of adjunction between the product and another functor, which would be some kind of function space. So what we want for the rest of the talk is that the double category of finite sets with the functions as vertical arrows, the relations as horizontal arrows, and the squares as coherence conditions is Cartesian closed for that precise definition. So this definition is related to the fact that it's a category object in CCC, but not quite. So it's a bit more complicated. So now we have this definition of parametric lambda term, which is related to the work of John Reynolds on abstraction of parametricity. So if we have a Cartesian closed double category and a simple type A, then we say that a parametric lambda term is the data of a family of vertical maps theta q, where q ranges all over objects. So this is the part on the left and on the right of this diagram. And a family of squares which connect all the vertical maps. So we have the squares theta r, which connects theta p and theta q. Okay, and now if we work out what this means in our precise example, because a map from the terminal object to any set is just a point of the set, it's the same as to say that we have an element theta q in the interpretation of A in Q, such that for any relation R between P and Q, the two elements theta P and theta Q are related, but not by R, by the interpretation of A at R. So this is some kind of analogy with a monoidal case, with monoids. And in fact, what we have is that the parametric lambda terms define a Cartesian closed category. So this shows that it's related to the lambda calculus in some way. And if we consider this type, which is the type that we have considered in the case of the church encoding, then the parametric lambda terms of this type are exactly, they are in bijection with the profinite words over the alphabet sigma. So this shows that the definition of the previous slide of parametric lambda term in the case of the double category fin set gives us what we already knew with profinite words. So to conclude about current future work, so we want to find a syntax for the parametric lambda terms in the deterministic model, which is the one I talked about in this talk, to understand more what phenomena can occur in this setting. We also want to explore more the parametric lambda terms in a model associated to non-determinism, and we already know that we have some kind of fixed points which are not possible in the case of the deterministic scenario. And we also want to see if we can have some generalization of logic on words, which is done with MSO on words, to some kind of logic on terms for the setting of higher order automata. So that's it. Thank you very much.